The other thing we're going to talk about this week is diagnostics in HLM, and we're going to use the HLM Diag package. Diagnostic assessment in general is done by taking a look at the residuals. And just as a refresher, the residual is defined as the difference between a model estimated value and the actual outcome. So it tests the y hat, what the model predicts, subtracted from the actual observed value. And what we want is for these residuals to be random. To put this another way, we don't want there to be some reason our model better predicts some values for some cases than other values in other cases, because this would mean that our model is somehow biased, misspecified, or contains outliers. In HLM, this presents a problem because our outcome is already correlated due to cluster membership. So our assumption about independence in the residuals is already violated. So as always, we have to separate out the process. We're going to do this with a process called upward residual analysis. And this starts by doing a level 1 analysis. And in the level 1 analysis, this is where we check our predictors. This includes both level 1 and level 2. And we'll talk about why this is shortly. And then we use the level 2 analysis to check our assumptions about random effects. It's recommended to start with the level 1 analysis and then move on to level 2. So level 1 residual analysis, also known as conditional residual analysis, is done by conditioning the residuals on their cluster membership. To put this another way, we estimate the residuals separately for each cluster. This is similar to doing a centering within cluster on the residuals. Essentially what we're doing is we're treating the random effects as fixed. So we're saying that we know the cluster that each observation belongs to, and we're using that to predict the actual outcome. The HLM Diag package provides flexible tools for doing these diagnostics with HLMs. And one of the key functions is this HLM resid function. This function has several arguments. The first is the object argument, which just specifies the model. Then there's the level argument, which specifies whether we want to do a level 1 analysis or whether we want to do a higher level analysis. We do this by specifying 1 for level 1 or the cluster identifier for higher level. So that's just our cluster ID. Then we have the type, which is least squares or empirical Bayes. Least squares is typically recommended for level 1 and empirical Bayes for level 2 and higher. Standardize is whether we want to check our raw residual values, our semi-standardized residual values, or our fully standardized residual values, and we'll talk about what these mean shortly. And what this does is it returns a data frame or a data set with the elements of the original model, including the predictors and variables, as well as the fitted outcomes. So here we're going to take a look at what the HLM resid package does. So first we fit our model, then we call the HLM resid, and here I'm doing level 1, type equals least squares, and I'm asking for the standardized output. And so you see what this gives us is a data set with the outcome and predictors, the raw LS residual, because I called LS, not empirical Bayes. This is the actual fitted value, and then the standardized residual. And so a lot of what we're going to do when we do these diagnostic assessments is a graphical assessment. Some of the plots we can make are fitted versus residual or outcome versus residual, and these are essentially the same, just the reverse of one another. We can also check predictors against the residual, and we could do normality checks, such as QQ plots, histograms, and density plots. So first we're going to take a look here at our fitted versus residual plot, and what we want is to see a nice noisy plot with a straight, smooth line. And so here I'm calling the qplot function with the predictor variable here, and then the residual value here. We can also check level 2 predictors with the same approach. And this is because we have accounted for our cluster membership already with our level 1 residual. So doing level 2 residual doesn't need that. It's already accounted the cluster membership is already counted for. There's no correlation within cluster because it's just the same value for each cluster. And so here we see again a similar result. We see a nice straight line. We don't see any real patterns here in this plot that would suggest that our residuals are somehow biased by this predictor variable. Another thing we can do is what's called the semi-standardized residuals. And what this is it can be demonstrated that in HLM, the variance of the residuals within each cluster is actually proportional to the leverage of that cluster on the model. And so that's what this 1 minus h is. This is the inverse of or it's 1 minus the leverage of the cluster on the model. So the variance of the residual is proportionate to that. And so if we divide that out, that gives us this semi-standardized residual. It's not fully standardized because we're not also dividing by the variance. We're just dividing by this leverage component. And this is good for checking the equal variance between cluster assumption. And so we can plot this as well. So here I'm calling the semi-standardized residuals. And here I'm checking the residual against the predictor again. And I don't see any meaningful pattern here. So I don't see any heteroscedasticity that arises as a result of this predictor in the model. And finally, we can do our regular normality checks with things like QQ plots. So we can use this ggplot QQ norm, which gives us a QQ plot. This line equals RLM gives us the line, and we see we actually do have some possible normality issues with this data. It does look like the residuals are not fully normally distributed, particularly in the tails. We can also check the level 2 analysis, and this is testing the random effects. So if we specify a cluster identifier instead of level 1 in the level argument, what this is going to do is it's going to give us all of our model estimated random effects. So this will either be the model estimated effects if we say empirical Bayes, EB, or it can be the separate least squares version. So this will essentially fit a separate regression for each cluster. This will give us our hierarchical model estimate for each cluster. So this will have shrinkage, if you remember a few lectures back when you talked about what was going on with the random effects. And so if we check this, we can do things like, again, check for normality. And here, so what I'm doing is I'm checking that the random intercepts are normally distributed as predicted by our model. And we see that this looks a little bit better. This point here is a little bit off the normality line, but for the most part, we're looking pretty okay here. One other thing we can do is called marginal analysis. And so marginal analysis essentially drops the random effects from the prediction. So it only uses fixed effects for prediction and then checks the residual between the fixed effects predicted value and the observed value. So essentially this is treating the model as a single level model, and everything you learned in single level regression applies here. The downside of this approach is that there's no way to diagnose which level problems may exist at, but this can still help diagnose something like nonlinearity in the data, and it may be a little bit more conceptually straightforward, especially when the actual sample clusters aren't of special interest, which is often the case in psychology. We're not often going to be interested in the actual sample that we're studying. Those units are not often going to be of interest for making our prediction. So this is another good approach, even though it can cause some ambiguity if you do detect problems. And you specify level equals marginal to get the marginal residuals. The last thing we're going to talk about is outliers and influence. And HLM-Diag also contains several functions to help assess influence, which includes Cook's distance, multivariate defits, coratio, RVC, and leverage. And these are all either the same thing or extensions of other statistics you've learned about in other classes that involve deleting observations and checking changes in either the data's covariance structure or in the model results. The difference is that in HLM, we can either delete a single observation at a time, or we can delete a whole cluster and check for that level of influence on the data. So we can do the level 2 version by specifying the group argument equals our cluster ID. And we also have a nice plot function in HLM-Diag called .plot_diag, which allows you to specify a cutoff value, which essentially draws a vertical line separating relatively low influence from relatively high influence. And the cutoff can either be specified manually, or you can set it to internal. If you set it to internal, it'll be 3 times the third quartile. And you also have to include the argument name equals, and then you have to use name the influence statistic you're using if you do the HLM-Diag plot. So here's what this looks like. So here I'm calculating Cook's distance, and I'm deleting by group, not by observation. And then I'm calling the dot plot. I'm saying x is the Cook's distance. The cutoff is internal, and I'm naming Cook's distance as the statistic I'm using. And then I'm just naming my y and x labels. And so here we get this vertical line, which is 3 times the third quartile, and we see we have several values that exceed this, and then we have one that really super exceeds it. And so these are all of some concern based on this sort of heuristic 3 times the third quartile assessment. And this one is probably really, really worth thinking about. This looks like a pretty major outlier. And so this is the paper that describes the HLM-Diag software in a little bit more detail. And so I encourage you to check it out as well.